Hi all. Today we can discuss about the similarity transformation and unitary transformation. So this seems to be very simple, but also difficult at the same time. Okay, so anyhow, in order to understand, to get a deep understanding about the similarity transformation. So first we can start with a simple example of a rotation of the basis vectors. Okay, so we can start with rotation of basis vectors in Euclidean space. So better we can take two-dimensional Euclidean vector space. So consider an example. Suppose you have a two-dimensional vector space I cap j cap, and suppose we have some vector here, vector A. Now this vector A can be written as AXI plus AYJ. Okay. Now, if you rotate this basis vector by some angle theta, then obviously we'll get another basis vectors. So you are rotating it by an angle theta, and the basis vectors that you are getting can be represented as I dash and j dash. So that the same vector, how will you write the same vector? The same vector can be written as ax prime I prime plus ay prime j prime, isn't it? Okay, and it can be written as vector a prime. So actually this vector a and vector a prime are same. So in the unprimed basis, we'll have its x component and y component, and in the primed basis, this length would be your x component and this length would be your y component. Okay, now anyhow we can write it as ax prime I prime plus ay prime j prime equal axi plus ayj. Now we can take the dot product with I prime. So if you take dot product with I prime, we'll get ax prime, I prime dot I prime. That would be ax prime. We'll get ax prime. That would be equal to ax I prime dot I plus ay I prime dot j. So I prime dot I would be the length of I prime multiply length of I, the cos of angle between them. The cos of the angle between I and I prime is theta. So this become ax times cos theta plus ay times what would be the angle between I prime and j, 90 minus theta. So cos of 90 minus theta. And sine theta. Then ay x prime is that. Then we can take the dot product with j prime on the first line. Then I prime dot j prime would be 0. Then ay prime, because j prime dot j prime would be 1. Ax times j prime dot I. So j prime dot I would be cos of 90 plus theta. That would become minus sine theta plus this will become ay j prime dot j prime dot j would be cos theta. Okay, so what we can write is ax prime is this, ay prime is this. So this entire thing can be write in matrix form as ax prime ay prime equal cos theta sin theta minus sin theta cos theta times ax ay. So the components of the operator transforms this particular fashion if you change the basis by the rotation of by an angle theta. Okay, so in another way, we can write as this A prime equal to some rotation about in some angle theta of A. So this R can be, we can call it as an operator. Okay, so this is the effect of the rotation of what we can say the basis vector. So remember this vector A and vector A prime are the same vectors, but on the different basis vectors in terms of different basis vectors. Now this can be connected through this kind of operation. So this operation will take this particular form if the basis vectors are rotated by some angle theta. But in general, we can connect two vectors. Okay, vectors. We can connect vectors with respect to two bases as we can write some alpha prime equal to some operator times alpha. Okay, so let vector alpha and vector alpha prime are two vectors in the same vector space, but on different bases. So they are represented in different bases. One is one basis, alpha prime is on another basis. Then alpha prime and alpha can be connected through this particular equation. So that is possible. Okay. There is again this is a generalization, n-dimension generalization. So in 2-dimension, suppose you have some vector alpha. So this vector alpha we can represent on unprimed basis and primed basis. So this the components of vector alpha and vector alpha prime can be connected through this particular way. Okay, now let us perform some operation on vector alpha, and that operation I am going to represent by some other symbol. Okay, so which is the best symbol we can choose. Okay, suppose this vector alpha transforms to vector beta by action of some operation, and that operation I am denoting as operator A. So let operator A acting on vector alpha gives vector beta. So this mathematical representation we have written in unprimed basis. Now how we can write the same mathematical equation in terms of primed basis? So when you're going to the primed basis, we have to transform it. Okay, so we have know that the connection between the alpha and alpha prime are represented in this way. Then how can we write vector alpha? Vector alpha can be written as S inverse of vector alpha prime. Similarly, how we can write vector beta? Vector beta we can write as S inverse of vector beta prime. If alpha prime and alpha are connected this way, then beta prime and beta would also connect in the same way. The S is a transformation operator. Okay, so since this is the case, I can rewrite our original operator equation as A times vector alpha can be written as S inverse of alpha prime, and vector beta can be written as S inverse of beta prime. Now we can take the product with respect to S from the left side, and you will get S A S inverse acting on alpha prime would be S inverse acting on beta prime. Now S times S inverse would be an identity operator. So what will you get? S A S inverse acting on alpha prime equals beta prime, or we can write as A prime times alpha prime equals beta prime. Okay, so this is the same mathematical expression, but in primed basis. Okay, so the transformation of vector alpha to vector beta in the unprimed basis, we can write as A acting on alpha equals beta. And in the primed basis, we can write A prime acting on alpha prime equals beta prime. Now, what is the connection between A prime and A? So this quantity is called the A prime. So this A prime is given as S A S inverse. So this transformation, the transformation of an operator from one basis to another basis is called similarity transformation. So this is the meaning of the similarity transformation. So this happens when the vector alpha and alpha prime is, so if the alpha and alpha prime is connected in this way, the vector alpha transform to alpha prime by the action of S, then the operator A transform to A prime A as S inverse. So this is what is meant by similarity transformation. Now the unitary transformation is just an extension of similarity transformation. Okay, so I think it is very clear now. So what we have started is, we have started with a simple example of two-dimensional vector space. So in two-dimensional vector space, we have just shown that the rotation of basis vectors changes the components of the vector. Okay, so if you have two bases, primed basis and unprimed basis, then the components in the primed basis and the components in the unprimed basis of the same vectors is connected through this kind of matrix equation. So that can be written in another way as A prime equal to RA. Now this concept can be extended to an n-dimensional vector space. Okay, suppose if you have two vectors, the alpha and beta. Now this alpha and beta can be expressed in terms of two different basis vectors, a primed basis and unprimed basis. Let us suppose their connection is this. The primed basis and unprimed basis are connected as alpha prime equal to S alpha and beta prime equal to S beta. And if the alpha and beta is connected through an operator A, that in such a way that the A acting on ket alpha gives the ket beta, then that is the mathematical expression of the transformation of ket alpha to beta in terms of unprimed basis. Now the same mathematical expression we can express in terms of the primed basis as A prime acting on alpha prime equals beta prime, where A prime is S inverse and alpha prime is S times alpha. So this transformation, the transformation of operator from one basis to another basis is called similarity transformation. Now what is meant by unitary transformation? So here we can just define what is a unitary transformation, and we can have the further discussion of unitary transformation in the next class. So unitary transformation is also a similarity transformation, but there is one extra condition. Unitary transformation has to preserve the Hermitian property of an operator. Okay, so unitary operation or unitary transformation is a similarity transformation which preserves Hermitian property of an operator. So that is, suppose you have an Hermitian operator, which is A dagger equal to A. Now you can transform this Hermitian operator A to another basis A prime, such that we can write this A prime equal to U inverse. Okay, so this A prime is an operator in the different bases. Okay, now if this transformation preserves the Hermitian character of the operator, then A prime dagger must be equal to A. So this transformation is called unitary transformation. If A prime dagger is equal to A prime dagger equal to A prime. Okay, so we can see then the condition on this operator U. So A prime is given as U inverse or A prime dagger is U inverse all raised to dagger. This would be equal to, according to the property of dagger, this become U inverse of dagger, A dagger, U dagger. Now A is Hermitian. Since A is Hermitian, I can write A dagger as A. So this would be equal to U inverse of dagger A times U dagger. Now this must be equal to A prime. So this must be equal to A prime means, okay, A prime is U inverse. So therefore, this, since it must be equal to A prime, which implies that U dagger must be equal to U inverse. Okay, because if it is equal to A prime, where A prime is U inverse, isn't it? So A prime dagger must be equal to A prime if A prime is a Hermitian operator. So therefore, we can write this equation must be equal to this, or U inverse raised to dagger A U dagger must be equal to U inverse. So this would be possible if U dagger equal to U inverse or U inverse raised to dagger equal to U. So this is a property of the operator U, which transforms A to A prime. Now this kind of operator is called a unitary operator. U is called unitary operator. Okay, so the operator which transforms in as per unitary transformation is a unitary operator. Okay, so unitary transformation is nothing but a similarity transformation. Only the extra condition is it has to preserve the Hermitian property of an operator. So if it has to preserve the Hermitian property, then this transformation operator must be unitary. So if A prime is U inverse in such a way that this transformation preserves the Hermitian characteristics of the operator, then this transformation is called unitary, and the operator U would be a unitary operator, such that is U dagger equal to U inverse. Okay, so the definition of unitary operator we can write in this way. The unitary operator U dagger equal to U inverse means U dagger times U must be equal to identity. That will also be equal to U times U dagger. So this is the more correct definition for the unitary operator. Okay, and we have discussed what is meant by the unitary transformation. Now there are certain properties for unitary transformations. Okay, the first thing is the eigenvalues of an operator will be unchanged under unitary transformation. The eigenvalues of an operator will be same. It will not change under unitary transformation. Okay, suppose you have some operator A acting on phi n gives lambda n phi n. Okay, so then if you have a unitary transformation such that is phi n transformed to phi n prime as u acting on phi n, then your equation would be the a phi n we can write as u a u inverse u on phi n equal to lambda n u on phi n. U acting on phi n would give phi n prime, u a u inverse would give a prime, the lambda n, and u acting on phi n gives the phi n prime. So the new equation, the eigenvalue equation in the transformed basis is simply a prime acting on phi n equal to lambda n phi n prime. So here under this transformation, the a phi n equal lambda n phi n. So under the transformation, when you're going to the new basis, the eigenvalues remain same. So the eigenvalues of the operator remain same under the unitary transformations. Okay, now what is the second property? The second property is the commutator would be same under unitary transformation. It means a prime b prime would also be equal to ab. So we can prove it. This a prime we can write as u a u inverse, and b prime can be written as u b u inverse. Okay, so this a prime b prime, the commutator a prime b prime equal to a prime b prime minus b prime a prime. So a prime is u a u inverse, the b prime is u b u inverse minus b prime u b u inverse and a prime u a u inverse. So this would be equal to u a b u inverse minus u b a u inverse. So this can be written as u times of ab minus ba times u inverse. So this will be u commutator a comma b times u inverse. So in most of the cases, the commutator a b would be simply a number. Okay, would be a complex number. So therefore, what would happen? So this is just a number. So this number can be taken outside. So this become the commutator a b u inverse or it is equal to the commutator AB. So this condition should be there in order to prove this commutator AB prime equal to AB if commutator AB equal to a complex number. So if it is an operator, then it is not possible. So certain operators, the commutator will become another operator. So in those such cases, this property is not valid. Next property, U A U dagger all raised to n is same as U A raised to n U dagger. So this proof is very simple. So U A U dagger all raised to n is the product of U A U dagger times U A U dagger up to U A U dagger. So we have to take the product of U A U dagger n times. Okay. Now there would be between U dagger U in between always. So U dagger U, since U is a unitary operator, U dagger U would be identity. So that would give U. Then here U A U dagger. So this would be identity. This would also be an identity. So we'll get A times A times A. There will be n A's, and finally on the right side there will be U dagger. So this is simply equal to U times A raised to n U dagger. Okay, so therefore it is possible to write the U of the f of A U dagger can be written as f of U A U dagger. That is f of, you can write it as f of A prime. So if you transform the f of A, where f of A is a function of operator A. So if you transform the function of operator A under unitary transformation, then this would be simply equal to the function of A prime. Okay. So because this is simply equal to A prime raised to n. Sorry, we cannot write this A prime raised to n. Okay, this is enough. So this is the fourth property. I think these the properties are enough for the time being. Okay, so we have defined what is meant by unitary transformation. So a transformation is said to be unitary if it preserves the Hermitian property of an operator. Then is in such cases, if A transform to A prime in the way U A U inverse, then this U must be a unitary operator. So these are for A prime under unitary transformation. U is a unitary operator. And therefore A prime we can write as either U A U inverse, or A prime can also be written as U A U dagger. So mostly the most of the textbook uses this notation, A prime equal to U A U dagger. So whether you write U A U dagger or U A U inverse, they are same because U is a unitary operator. And we have discussed the different properties of the unitary operator. The first one is it does not change the eigenvalue of an operator, and the commutator also preserves if the commutator is equal to a complex number or just a scalar. And U A U dagger all raised to n is U A raised to n U dagger. And if you transform the function of an operator, that is also same as the function of transformed operator. Okay, A prime is a transformed operator where A prime is U A U dagger. Okay, so that's all about the similarity transformation and unitary transformation. And this kind of transformation we required frequently in quantum mechanics. And this transformation would be very helpful to simplify our problem. So if you transform the basis into more convenient basis, the problem will become very simpler. So that is the main idea. Okay, so those things we'll come to know when you are going to use the representations. We can see the power of unitary transformation for simplifying our problems or mathematics. Okay, so that's all for the time being. So we can stop it here. In the next class, we can discuss two types of unitary transformation: the infinite unitary transformation, finite unitary transformation, and we will see a, an explicit expression for our unitary operator. Okay, so thanks for time being. Thanks for watching this video. We'll see you in the next class. Bye.